Hello, my name is Jenna Nichols, and for structure 1.3.5, we're going to talk about essentially everything you need to know about electron configurations. So let's do a very quick review of what an orbital is. An orbital is the region in space around an atom where an electron is likely to travel. So we have three shapes: S, which is a sphere, P, which is three different orientations of dumbbells. We have an X, Y, and Z. Usually the Z will be up and down, but just X, Y, and Z, three different directions of the dumbbell shape. You will have d orbitals, which are like these weird flower things. And then you have a dumbbell donut, which is, there's 5 d orbitals in a particular sublevel. And then I'm not going to even attempt to draw F, but there are 7 different orbitals per sublevel for F. And they're just even crazier shapes. So again, orbitals, areas of space, 3-dimensional, where an electron is likely to travel in a particular energy level. Now, there are 3 rules for electron configurations that we're going to go over today. The first one's called the Pauli exclusion principle, and it basically says that each orbital can only have 2 electrons, and they will have opposite spin. So we will frequently draw orbitals as boxes, so like the 1s orbital. Each orbital, each box, can hold 2 electrons. We represent those electrons with arrows. So there's our first electron. If there is a second electron present, it must have the opposite spin. So it will have a down arrow. And so that's what the Pauli exclusion principle is. They must have opposite spin for the 2 electrons in a particular orbital. Now, an orbital diagram shows all of the electrons in a particular atom. So let's say I want to do lithium. Lithium has 3 electrons. So the first 2 electrons are in the lowest energy level. And so it would look like that, one of each direction because of the Pauli exclusion principle. And the third electron would then go in the next highest energy level. And sometimes you'll see orbital diagrams like this where they're ordered from lowest energy at the bottom to highest energy at the top. Sometimes you'll just see them laid out in order like this. So this would be 1s, 2s, 2p. And then P, D, and F, since there are multiple orbitals in each sublevel, you'll see those boxes together. And let's be really clear on a couple terminology things. So this is an energy level, because it starts with the principal quantum number 1, first energy level, second energy level, third energy level. Then if we're looking at sublevel includes all of the ones with the same shape. So this is the 2s sublevel, the 2p sublevel, 3s sublevel, 3p sublevel. Within that, then we also have orbitals. This is a 3s orbital, 3p orbital, 3p orbital, 3p orbital. And we will typically label the p orbitals in order X, Y, Z for those 3 different orientations. Now, the second of our rules for today is called the Aufbau principle, and it states that you always fill in electrons from the lowest energy to the highest energy. So you'll always start at 1s, completely fill the 1s before you go on to 2s, completely fill the 2s before you go on to 2p, completely fill the 2p before you go on to 3s, etc. So lowest energy to highest energy. And this is a good time to point out that when all of the electrons are in their expected location based off of the Aufbau principle, that's what we call the ground state. If you had a gap like here and it was somehow up here, this would be an excited state because one of the electrons has jumped to a higher energy level than expected. So that would be the excited state. So our third rule is Hund's rule, and it only applies to degenerate orbitals. So it only works for P, D, and F. And that's because it has multiple orbitals at the same energy, which is what we call degenerate. So all of these orbitals in that 2p sublevel have the same energy, so they're degenerate. Hund's rule states that you will spread out the electrons among the orbitals that have the same energy. So let's say I've got, that would be boron with 5 electrons. But if I have carbon, 6 electrons, I need to put the next one in a different p orbital because the electrons always spread out. So you have 1 electron in each of the p orbitals before you double up. That's Hund's rule. So that would be carbon, nitrogen, oxygen then has 8. So you can start doubling up. So 1 in each before you double up. And then fluorine, and finally neon would have 10. Same thing when you get a little higher. You add a 1 to each of the p orbitals before you double up. And then if you get to the d sublevel, you will have 5 orbitals in a d sublevel. You would need to put 1 in each of those, all 5 spread out before you start adding the 6th, 7th, 8th, 9th, 10th in that order. Okay, now we can use the periodic table to help us figure out the order to fill our orbitals. Effectively it tells us about Aufbau principle. The very lowest energy orbital is the 1s, and so you can use hydrogen as our starting point with 1s. Helium also has 1s. So those 2 electrons in the 1s is part of the reason why this section is 2 elements wide, 2 electrons in the s orbital. So after helium, we've got this 2s for lithium and beryllium. And then when it moves across, now we're in the p block. The p block is 6 elements across. So we've got all of these are the 2p. So you would fill up the 2p. P can hold 6 because of the 3 boxes. You can hold 6 electrons in the sublevel. Now after 2p, we're going to come back to s, 3s, and then we go across in order to 3p. And then the next period, 4s. Then we get into our D block. The D block is 10 elements across, and it starts at 3d. And I know that's kind of weird, but you have your S block that starts at 1. P block here starts at 2, and our D block starts at 3. So it does go in order. Just use the periodic table to know the lowest energy to highest energy. So 4s, then 3d, and then it goes back to 4p. Then we have 5s, and then 4d, and then 5p. And it does keep going. You don't really need to know for the IB curriculum any further. And really, you only need to know up till krypton, which is 36. But I wanted to show you that the same pattern does occur for that 5th period. But if you know up through krypton, you are solid for the IB exam. So again, in order: 1s, then 2s, then 2p, then 3s, then 3p, 4s, 3d, 4p. So use the periodic table as a tool to help you remember using those S, P, and D blocks. So let's pull it all together. On the periodic table, we start with the lowest energy. For our hydrogen is in 1s, so our first electron needs to go in 1s. And hydrogen and helium make up the 1s section of the periodic table. So the first 2 electrons are going to go into 1s, upspin, downspin. That makes up the Pauli exclusion principle. After 1s comes our 2s. And if we have 2 electrons for it, you're going to fill it 1 up, 1 down. After 2s comes the 2p. The 2p sublevel has 3 orbitals. and you will put 1 electron in each before you double up. That's Hund's rule. After 2p comes 3s, and after 3s comes 3p. Again, 3 orbitals, 1 electron in each before you double up. After 3p comes 4s, 1 electron in, of each spin, and after 4s comes 3d. These are really wide, but there's 3d. You will put 1 electron in each before you double up. And then finally, after 3d will come 4p. 1 electron in each before you double up. And so that is your the extent that you need to know orbital diagrams and the order in which you need to fill in electrons into an orbital diagram. Now, it's a whole lot of work to be drawing all of those boxes and arrows, so chemists have developed kind of a shorthand for this. So let's do a short one. We'll always go in order. Okay, so this is oxygen. Oxygen has 8 electrons, and they're organized like this. This orbital diagram might still be useful occasionally, especially to show how the electrons are arranged in the 2p sublevel, but the shorter version, or what we call the full electron configuration, you change the number of electrons to a superscript. So this is 1s2, because there's 2 electrons in there, 2s2, 2p4, because we have 4 electrons in that sublevel right there. That would be for oxygen. Let's do one more quick example. Let's say we have sodium. Sodium has 11 electrons. That's 10, 11. So the full electron configuration for sodium would be 1s2, 2s2, 2p6, 3s1. You do need to write 1s to indicate the 1 electron. And then we also have something called a condensed electron configuration. Some people also call this the noble gas configuration. So let's go back to, let's say, lithium. Lithium has 3 electrons. So its 3 electrons are organized like this. So its full electron configuration would be 1s2, 2s1. But the first energy level is completely full. So it has 1 valence electron in the outermost level. This inner shell, completely full, is just like an atom of helium. So another way that we can write this is by saying it's helium with another electron in 2s. And so this is the condensed structural formula. Let's look at another one. Let's say I have, let's go back to oxygen again. Oxygen has 8 electrons. Oops, I went one too many. 8 electrons, 1s, 2s, 2p. Again, its first energy level is full, so I can say that it's effectively like helium, but with 2s2 and 2p4 in addition. So the benefit of this is that everything outside of the brackets is the valence electrons. Lithium has 1 valence electron, oxygen has 6 valence electrons. Let's look at a bigger one. If I've got aluminum. This time I'm going to, well, I'll draw it. Aluminum has 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1s, 2s, 2p, 3s, 3p. Its full electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p1. Now its first 2 energy levels are completely full. Well, that's just like neon. Neon has 10 electrons perfectly full. So you can also write aluminum as saying, okay, it's like neon, but it also has 3 valence electrons in addition to neon. So 3s2, 3p1. This is the condensed or the noble gas configuration for aluminum. So let's talk for a second about 4s and 3d. 4s, 3d. D can have 5 orbitals, so 10 electrons. The 4s and the 3d sublevels are very close in energy, much closer than some of the other orbitals that we've looked at. So sometimes when we are writing these electron configurations, you're going to see that some people will write like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. I'm assuming everything before this is full. Some people will write it 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. To keep the third energy level ones together. And so you might see either one of those because that 3D and 4S are so close in energy. So that's really important to remember. Part of the curriculum for IB that makes this important is that in the 3D sublevel, right? In that 3D section on the periodic table, we have what's called the transition metals. And the transition metals are called transition metals because they can have different oxidation numbers. So they can form ions of different charge. And that's because of the closeness in energy between 4s and 3D. So it has different ways that it can lose those electrons and still be relatively stable. And we will look at that in more depth as we go on. But right now, you just need to know they're very close in energy, which can lead to the transition metals having some different charges. Okay, so now we looked at the normal order of operations for the Aufbau principle in order on the periodic table. And so we typically would do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. In that order. Now there are 2 exceptions. There's actually more than 2 exceptions, but there's only 2 that you guys need to know, and that's copper and chromium. Copper, well, let's start with chromium first, actually, because chromium has 24 protons, 24 electrons. Chromium is 1s2, 2s2, 2p6, 3s2, 3p6 for the first 18. And then how it works for chromium is that it has 4s1, and 3d5. All right, so let's look at that in a little more depth. You would usually expect the 4s and 3d, 4s, 3d. So it has 24. You would normally expect those extra 6 electrons to go 1, 2, 3, 4, 5, 6. But because the 4s and 3d are very close in energy, that one of the electrons in the 4s is more likely to fill up the 3d with 1 electron in each. That makes the electron configuration half full orbitals for all of those orbitals, which makes it pretty stable. So you do need to know this weird electron configuration for chromium. And copper follows a very similar pattern. Copper has 29. So 1s2, 2s2, 2p6, 3s2, 3p6 for its first 18. And then after that, we have 4s1. Write that better, 4s1, 3d10. Now again, normally we would expect 4s to be completely full. For those extra 11 electrons, you would expect this, 3d and 4s. But because the 4s and the 3D are so close in energy, one of the electrons is more likely to fill up that 3D sublevel, Pauli. So that way the 3D orbital is completely full. That makes it very stable, and leave just one electron in the 4s orbital. So you do need to know these two exceptions to the rule. Chromium ends in 4s1,3d5, copper ends in 4s1,3d10. Okay, let's talk about ions really quickly. Let's say you've got something like sodium. Sodium has 11 electrons. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sodium is a metal, so it's likely to lose electrons. The reason why it's likely to lose electrons is because this is its core energy level. So the 1s is completely full, and then the 2s and 2p, second energy level, is completely full. It just has one valence electron. Anything that has less than 4 valence electrons is very likely to lose those valence electrons. So when sodium loses its valence electron, and you wind up with a sodium ion, it's effectively you're going to lose that outermost energy level. So you'll wind up with just 1s2, 2s2, 2p6. And so anytime you're forming positive ions, you want to take away valence electrons from the electron configuration. Now for negatively charged ions, let's look at oxygen. Oxygen has 8, 1s, 2s, 2p. Oxygen looks like this. 1, 2, 3, 4. So that's oxygen. Oxygen's a nonmetal. It likes to gain electrons. And the reason why it wants to gain electrons is because it has 6 valence electrons. 6 valence electrons, that means it's only 2 away from filling up its shell and becoming like neon. Full orbitals are very, very stable. So if it gains 2 electrons, it's going to gain them in this outermost level here, like that. And so the oxygen tends to form 2 minus charges because it gains 2 extra electrons. So it would be 1s2, 2s2, 2p6 is the electron configuration for a negative ion. You would add electrons to the valence shell to make your negative ion. Okay, so let's look at an example. We'll draw the orbital diagram for aluminum. So 1s, 2s, 2p, 3s, 3p, 13 electrons for aluminum. Pauli exclusion principle, 1 up arrow, 1 down arrow for each. Hund's rule, you have to fill in 1 in each before you double up. And there are the 13 electrons for aluminum. So our full is 1s2, 2s2, 2p6, 3s2, 3p1 for aluminum. And the condensed electron configuration, we can ignore the neon electrons, and we just show the valence electrons. Okay, so for iron has 26 electrons. So we're going to go 1s2, 2s2, 2p6, 3s2, 3p6 to get our first 18, and then 4s2, so now we're at 20, and we need 6 more electrons to get to 26, so they will go in the 3d, 3d6. The condensed one, we're going to basically ignore the argon, the first 18 argon, and just show the valence electrons, or the outermost 4s2, 3d6, like that. Last example, let's look at an ion, zinc 2+. Let's go ahead and write the normal one first, 1s2, 2s2, 2p6, 3s2, 3p6, it gets us to 18. 4s2, 3d10 gets us to 30. So that is the normal zinc. Now when zinc forms an ion, it's going to lose 2 electrons because it's positively charged there. Now remember that the 4s and the 3d are very, very close in energy. So for zinc, it's more likely that it will lose the electrons from the s orbital instead of just losing 2 from the d orbital. This leaves the d orbital intact with 10 electrons completely full. So you wind up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 for that zinc 2+ ion.